Hi everyone. Today we're going to talk about angular kinematics, and this is going to be our first video in chapter 10, rotational mechanics. So the reason we're going to call it angular kinematics instead of rotational mechanics today is because we're going to talk about the general kinematic equations from last semester, basically the foundation of um, physics in the linear world. And now we're going to spin all of it, and we're going to talk about the relationships that all of that has there. So we all live in a rotational world. These titles get punny a little bit. So let's talk first about kinematics. Okay, kinematics. We have the linear position, velocity, and acceleration. Right. X can mean distance. It can also mean displacement. And we'll talk a little bit about that later. But in angular terms, you've got angular position, angular velocity, and angular acceleration that are a direct translation of that. So those you can actually put in, and we'll do that in the next video. We will just replace any x, v, and a with a theta, omega, and alpha at any time, so that you can translate that from linear kinematics to angular kinematics. Okay, next you've got F equals ma, right? And the summation of force equals the derivative of momentum. Remember, if you take the derivative of momentum, you could either get dm dt times v, or you could get m times dv dt, which is a, right? So that holds true. Now, torque. Now, when I write this tau, this is a weird font, so it kind of gave me a weird tau, but this is how I'm going to write my taus for torque. But torque is going to serve as our analogous angular force. It's not a perfect analogy, but it's what we're going to go with because the math actually lines up, because you've got angular acceleration right here, and then angular mass is kind of weird. Angular mass is called moment of inertia. We don't call it angular mass. That's not a real thing. But moment of inertia can actually serve as mass in some of these analogous formulas. We'll talk about moment of inertia extensively later, but it's basically the idea that mass has inertia, right? It's just a characteristic of mass that it either wants to keep going the way it's going and it doesn't want to slow down or change direction, or it's the idea that it doesn't want to start moving, right? And you actually make it move from rest, right? Newton's first law. Moment of inertia is the similar idea that any mass resists rotation, right? And we'll talk about that extensively later. Now we also have the summation of torque equals dl dt, right? So dl dt, L, if you actually look over here, L is our angular momentum, right? You've got, pushed a button. You've got linear momentum, angular momentum. You've got mass, angular mass, right? Moment of inertia, then velocity, angular velocity, right? Direct translation, just like from the other kinematics. So if summation of force is the derivative of momentum with respect to time, summation of torque is the derivative of angular momentum with respect to time. So that is also direct translation. And then here we have rotational kinetic energy. I haven't talked about this yet, but we will this chapter. 1/2 obviously stays 1/2, but when you see that m, it goes to moment of inertia. Where you see that v, it goes to omega, right? So you've got a lot of direct translations all throughout this chapter. Now, there is something called Malaysian gassing. Malaysian gassing is an interesting sport or an event, a game, I'm not sure. But it's kind of like Beyblades. If you look over here, there are these handcrafted tops that have this really long string on them. It's almost like a whip. But when you spin this, they actually launch these tops at one another. The rules look kind of like curling, right? Where one person puts their tops down and then you take turns hitting them back and forth, right? But this has some really interesting rotational mechanics to it. So if you can find a YouTube video, I can't really pull that YouTube video up now. That's an easy way to get your YouTube video taken down. But look up Malaysian gassing. It's a really interesting. I think it's a sport that they play in Malaysia, but it's all about rotation, right? A lot of rotation in there. Right, so today we're going to talk about angular kinematics, like we said. We're going to talk about angular position, angular speed, and angular acceleration. So if we look at the 2 marks on this spinning wheel to the right, okay, we have an initial point here, and then you have your final point here, right? If you want to describe the change in position, would you use S, the arc length, or you would use the angle theta to describe its change, right? So let's look over here. As the disk rotates, a particle P moves through an arc length S on a circular path of radius r. The angular position of P is theta. So that already told you that the position is theta, right? But the reason we use theta instead of S, right? If you have circle with radius r, and then you've got this S, right? Say it moves some angle theta, and that arc length is S. Now, if you have an even bigger circle with an even bigger radius. Now, if it were to move the exact same angle, that theta, okay, let's call this theta 1, okay, S1, R1, and then you've got R2, S2, and then you've got theta 2. But theta, the thetas will equal each other, right? You can see that it moved the exact same angle, right? The radius, however, is longer, and then that makes the arc length longer. So if you use arc length to measure angular position, it's going to rely on the radius of the circle. But if you use theta, it doesn't matter what the size of your disk or your rotating object, the radius doesn't matter at all. If you use theta, your math is going to be consistent for every object, regardless of its radius. So that's why we will use theta to measure angular position. Now let's talk about what you measure that position in. Okay? We're going to measure that in radians. So first, let's talk about what is a radian, right? So a radian is the angle. Yeah, my stuff's loading. A radian is the angle that you make if you were to take the radius of a circle. Let's do this. Okay, you've got the radius of a circle, and you were to overlay that radius onto the circumference. Okay? That angle that you make if you take the radius of the circle and overlay it onto the circumference, that angle is 1 radian. Okay. Now, the reason we use radians, well, that's jumping ahead. So that's what a radian is, right? That is the angle that you make if you were to take the radius of a circle and use that as an arc length along the circumference. The angle you make there is 1 radian. So we can actually show how many you've got in one circle, right? If you say the circumference of every circle is 2 pi r, right? But if 1 radian uses 1 radius as an arc length, let's divide the circumference by the arc length. So if you take 2 pi r, divide that by the radius, you get 2 pi radians in every circumference, okay? Because every circumference is 2 pi r. And if you divide that by the radius to see how many radians you could get, right? Because remember, radians rely on 1 radius along the circumference. You would get 2 pi radians for every circumference of every circle, regardless of the radius, right? Because the radii cancel. Now, if you want to know what 1 radian is in degrees, okay, 1 radian, if you take 360 degrees and divide that by 2 pi, okay, you get 57.3 degrees. Okay, that is what 1 radian is equal to in degrees. Now, we're going to kind of abandon degrees for most of this chapter, if not all of this chapter. The only reason we would use degrees is if the problem gives us degrees and we got to put it back into radians. But 1 radian is 57.3 degrees. Multiply 57.3 by 2 pi, you're going to get 360 degrees, right? Now, the next question asks, how many radians do you have in each revolution? Well, we kind of answered that already. Each revolution is 2 pi radians. But the reason this is something that I want to I really want to harp on, and I want to make sure that we are clear on this, is because you will get information in revolutions per minute, revolutions per second, or they'll ask you for your answer in revolutions per minute or revolutions per second. To make that unit conversion, you've got to say that 1 revolution is equal to 2 pi in your angular position, right? It is 2 pi radians. And then what is the unit for radians? So this is where things get tricky. Radians is an artificial unit, okay, that we use to define angles. Now, to measure a distance, it doesn't really work because radians are called non-dimensional, okay? They are not dimensional. They don't travel just in one dimension, okay? We actually disregard them when we do dimensional analysis. Right, so say we have, we're traveling at something spinning at 3 revolutions per minute, and you want that in velocity. You would actually say that, oh, whoops, I want that to be multiplied. Okay, 1 revolution would be 2 pi. So that revolution goes away, but you wouldn't include radians. So you would actually say that this is 6 pi per minute. And we'll actually talk about that in our next slide when we talk about angular speed, but you kind of disregard radians when you talk about them in units because they're dimensionless. Now, it's not incorrect to say this is 6 pi radians per minute. You just need to pick one of those conventions to use and stick with it throughout your entire problem. But it is customary in physics to sometimes use your velocity and your acceleration in the angular world without radians. And we'll talk about that more later. Now, why do we use radians instead of degrees or revolutions? So the reasons we do that is because calculus is basically in radians, right? When we do our kinematics, when I said earlier that we'll just replace x with theta, v with omega, and a with alpha, that's going to give you an answer in radians. The answer that you get, this number, the number doesn't make sense if you put it in degrees, right? Or if you put it in revolutions, the number just doesn't simply make sense. But the number is in radians, and that's why we're going to use radians throughout this entire chapter. And if we get revolutions or degrees, or they ask for it in revolutions or degrees, we're going to have to convert back and forth. But all of our math should be in radians, because that's simply how the math works, right? Our kinematics and our calculus are all built with radians in mind. So that's why we're going to use radians. Whoops, I've got an eraser right now. Okay, that's embarrassing. That's why we're going to use radians instead of degrees or revolutions. All right, next, we've got angular speed. That's used with this omega. I draw my omega like that. It is a curly W. Now, we want to write the equations for instantaneous and average angular speed for a particle moving on a wheel. So we've got a wheel over here that it's talking about, right? So if we want, let's look at linear first, right? Linear average velocity, or you could say v bar, okay, that was just delta x over delta t, okay? On average, you have to travel this velocity during this amount of time to travel this distance, right? That's just your average. If you want your instantaneous velocity, you need to do either derivative or a limit, right? You take the limit as t approaches 0 of delta x over delta t, and that gives you dx over dt, right? You need the derivative or you need a limit. You need some complex algebra to get instantaneous information. Now, if you want to get this information in angular world, what you do is you substitute out your v's and you put in an omega. average angular speed, delta, oh, whoops, that's delta theta over delta t. This would be instantaneous omega is delta theta over delta t. So we're just going to make that a direct translation. And these are the equations that we are going to use if we need instantaneous or average speed in the angular world. Now, what are the units for angular speed? So this is where things get interesting. The units for angular speed are technically radians per second. However, this usually is shown as second inverse, which is 1 over seconds, because we don't usually write down radians as an official unit. That's just the custom that I've always used. That's the custom that I was taught. That's the custom that our textbook uses. You usually just stick with inverse seconds. Now, it's understood that when you say inverse seconds, you're talking about radians per second. You're not saying degrees per second or revolutions per second. It's just understood that it's radians. That also helps you remember that this is not meters per second, right? This is not linear. It is angular. So you would say inverse seconds. And that's because, like I said, radians are dimensionless. They don't fit in dimensional analysis. So we kind of ignore them when we talk about speeds, velocities, and accelerations. All right, now angular velocity, right? We've been talking about angular speed. Not often do we use speed instead of velocity in physics, right? So if we want to talk about angular velocity, that requires a direction, right? The difference between velocity and speed is that velocity is speed that's going somewhere, right? It's got a direction. So, for example, if an object rotates in the xy plane in the counterclockwise direction, what is the direction and sign of omega? So if you are rotating counterclockwise, okay, you've got an object rotating counterclockwise, okay, that would be positive omega, okay. Now the direction is a little complicated. It's obviously not rotating like left or in the positive x or the positive y, right? Because it's in both. It's constantly in both, other than, you know, at these very specific moments where the tangent velocity might be in one specific axis or one specific dimension. But that omega is going to constantly be spinning, and you can't say that's positive x or positive y or negative x or negative y, because it's constantly, I mean, at any given point, you could choose one point and say that's positive x rotation, but you could choose another point and say that's negative x rotation on that rotating disk. So what we use for direction is the z-axis. So if it is rotating in a positive omega direction, the direction is up. If you're in the xy plane, you have an up rotation or an up direction. Now, number 4 asks, so is clockwise motion positive or negative angular speed? So that would be a negative angular velocity if you're going clockwise, right? So if you go clockwise, your direction is also down instead of up. And this is used using the right-hand rule on number 5. It says use the right-hand rule for direction in z-axis terms. So if you use your right hand and you curl your fingers, okay, your fingers are pointing in the direction that your object is rotating, right? Whichever direction you're using. If it's going counterclockwise, okay, using your right hand, your thumb points at you. Or if you put it in the xy plane, okay, assuming the xy is flat, your z or your thumb is pointing up. So that means that your direction would be up or positive. Then if it's going clockwise, your thumb is pointing down, so the direction would be down the axis or be negative. So interesting for angular velocity is that the direction is actually along the axis of rotation, or in the direction of the axis of rotation. It's not actually anywhere on the disk at all. So that can be confusing. But that's how you can get around the fact that this point right here, technically moving, if we go by conventional xy direction, that is negative x, right? But this is positive x. But how could 2 points on the same object be rotating in opposite directions? So that's our way of solving that, right? You've got positive y and negative y on that wheel also. So your solution is a direction that's completely separate of those axes altogether. Now, last slide we've got is angular acceleration. Okay. Angular acceleration, we want to describe two different ways to produce negative angular acceleration on this spinning wheel. So we want negative angular acceleration. Okay. Now, remember the negative direction is clockwise. Okay. So if we go clockwise and we speed up, okay, that would be negative angular acceleration. Or if you were going counterclockwise and you slow down, that would also take negative angular acceleration. Similar to linear acceleration, right? If you were going in the positive x direction, say you're going, let's say positive x is right. Okay? Say you're going to the right and you're accelerating, that's positive acceleration. Or if you're going to the left and you're slowing down, that's also positive acceleration, right? So nothing new, just the idea that clockwise and counterclockwise are now the directions that we're talking about, and the direction of angular speed is now up and down, not in a circle. All right, number 2 asks us to write equations for instantaneous and average acceleration. And why is this not very new? So instantaneous and average. So we've got average alpha or alpha bar. Okay, that is just the change in omega over time. That's not a very curly omega. There you go. And then if you want instantaneous angular acceleration, you can do the limit as t approaches 0 of delta omega over delta t, which gives you d omega over dt, right? That's basically the exact same equations we used for velocity as well, and it's the exact same equations we used for linear acceleration, right? So all we're doing, again, is just taking the angular counterpart and putting it in for the linear counterpart in their equations. Now, what are the units for angular acceleration? So here, the unit could be read as radians per second squared, or you would write this as s to the negative second power, which, you know, kind of translates to 1 over second squared. You kind of ignore that the radians are even there because they have no dimension, so they don't really belong in dimensional analysis. Now, you're not wrong. Like I said, you're not wrong if you put radians per second squared, as long as you're consistent throughout your entire problem, and as long as you know your audience. If you know your professor, your teacher prefers one way or the other, stick to that. Now, how will the following compare for two particles at different radii on a spinning wheel? So let's look at a spinning wheel. I know I don't make the most perfect circles, but try. That's not bad. Okay, so we've got a radii here. Okay, we've got point P, we've got point Q, and it's going to rotate and then we've got another P. We'll call this P2 and Q2. Okay, 2 different positions. Now, we're on a spinning wheel, right? Now, this is usually, you know, I've got slide transitions and everything, so this is usually much cleaner, and you can't see the answer already. But if you can see here, linear velocity and linear acceleration, that's going to be different for each of these. Now, if you look here, that Q, oh, I flipped the P's and the Q's. That's embarrassing. So the Q is closer to the center. Right? It's closer to the center of the circle than P. That means that P, if you can look at the arc length, obviously has longer to go, right? So if they're going to make that rotation at the same time, assuming this is a rigid object, right? You know, the outer edge of your CD doesn't like have to catch up to the inner part of your CD, right? If you follow that radius, if you draw, like make a line on your CD and make it spin, all points along that line are going to spin all together. But that means that the further you are out on that line, you actually have to go faster than you are when you're closer to the center. So your velocity is actually different for 2 points to have a different radius. However, if you've got angular speed or angular velocity and angular acceleration, those are going to be the same. Because if you look here, if angular omega, right, angular speed is the change in theta over the change in time, right? Well, this angle theta here, okay, let's say that's an angle. They both traveled the exact same angle, and they did it at the exact same time. So that means that their delta theta was the same. That means their delta t is the same. So therefore, their angular speed would be the same. Then if their alpha is delta theta over delta t, well, they're going to have the same omega. They're going to have the same angular velocity, which means that they're going to also have the same angular acceleration, right? If they have to change their angular speed, they have to do it at the same rate. Because if you do it any faster, then all of a sudden your disk is going to start warping and then your disk breaks, right? So when things are spinning, your linear quantities are going to be different depending on where you are on that rigid object. But if you have a rigid object spinning, your angular components are going to all be the same no matter the radius, which is the beauty of angular kinematics. All right, that is going to wrap up our episode here. And tomorrow, or on the next video, we're going to talk about the angular kinematic equations and how those translate from the linear equations.